Welcome to the fourth tutorial in this series on quadratic functions. We spent the previous tutorial looking at the quadratic formula, which is quite an ugly beast, it has to be said, and it will give you the values of the roots of a quadratic equation. Namely, if someone gives you a quadratic function and the values a, b and c, you can plug them into the quadratic formula and it will tell you, assuming the roots exist, where those roots are. Now, I want to talk about quite a different topic in this tutorial. It seems to be one that students don't like very much. I'm not sure if it's because the way it's typically taught, I'm not sure. But I have to say, if there was one thing that you had to know how to do with quadratic functions and you weren't allowed to know anything else, this would be the thing to know, because if you know this technique I'm about to teach you, you can do anything you like with quadratic functions. And that method goes by the name of completing the square. In principle, you could rethink the whole teaching of this topic and just teach completing the square, because you can get all information about a parabola from this method. Let me just show you the notes from a previous tutorial where we talked about the nature of the roots. And do you see how yes, sometimes there are roots, and the quadratic formula that we used in the previous tutorial is kind of a rather hand-turning way to put numbers in. It's kind of like a sausage machine. You know, you put the meat in one end and you get the sausages out the other and you get your values of the roots. I don't think it's terribly satisfying. But look, there are going to be examples where there are no roots, but there's still information there. What's the axis of symmetry? What are the coordinates of the turning point? How do we describe these parabolas if there are no roots and we can't use the quadratic formula? Well, the answer to that plea is, don't worry, just complete the square. This is sort of the prince of methods in this whole topic of quadratic functions. It's actually quite straightforward, but as with all things, needs a little bit of practice. So this is definitely something which is best taught by example. So let's just do an example. And in fact, let's look at the quadratic function we saw in the previous tutorial. Y equals x squared, take away 2x, take away 8. Okay, so there's a very nice quadratic function. Now we happen to know, because of solving for the roots, that this has roots at, I believe they were at -2 and 4, and we even used that information to figure out where the axis of symmetry was, because the axis of symmetry, if there are roots, will always lie midway between them. So we happen to know that the axis of symmetry, or the mirror for this parabola, is at x equals 1. But let's pretend that we don't know any of that, and let's just say we only know one method with quadratic functions, and it's completing the square. What does that mean? Well, here's how you go about this. When you complete the square, your first step is ignore the bystander. Let's call that constant that gets tacked on the end of a quadratic function the bystander, and I want you to ignore it at first. We're just going to concentrate on the first two terms. Okay, and our aim is to write these terms as something squared plus a constant. That's our aim. And you might say, well, why do we want to do that? And the answer lies in the first tutorial. Do you remember that when we looked at parabolas that had the form ax squared plus c, how easy life was? You know, we had the symmetry about the y-axis. It was so easy to sketch these curves. Life only gets hard when this pesky bx appears, okay? So, the aim with completing the square is, I would say, a more mathematical, a more sort of intuitive aim than any of the other things that we've talked about so far. It's to say, life was easy when we just had ax squared plus c. Let's make our more sort of scruffy quadratic function look like something squared plus a constant, because then it would be so easy to interpret what it looks like. So the negative 8 here is already a constant. That's why we sort of ignore it at first, because that's not going to be a problem. This is the pesky term, and we have to figure out a way to sort of absorb this like an amoeba would absorb a bacteria, to make just something squared, and then life will be so easy. And we want to make this look like x plus or minus a number all squared plus a constant. So let me just kind of tell you really what essentially, to be honest, it's a trick. There's nothing deep here. It's really a trick. What you do is the following. You take x and you take the number multiplying x here, and you multiply it by a half. That's it. That's the whole method, is taking this number, multiplying it by a half and putting it in this bracket. So negative 2 times a half is negative 1. That's what we're going to square. And now we have to do something a little bit awkward, which is the following. We want these two things to be equal, but they're not equal at the moment. Why not? Because x take away 1 all squared, let's just look at that. What is x take away 1 all squared? It's x minus 1 times x minus 1, which is x squared minus x gives us minus 2x. Good, that's what we wanted. But look, this term gives us plus 1. But we don't want plus 1, we just want x squared minus 2x. So when we do this, we get one bit too much and we have to subtract it off. So that plus 1 has to be then removed explicitly by taking negative 1 from this square. And then these two things are equal. Therefore, we can write this original quadratic function as x squared minus 2x, okay? That we have shown is just x take away 1 all squared minus 1. And finally, at this last stage, you bring back the bystander, negative 8. We just bring that back. And you see it just tacks on as an additional constant to this little correction piece we had to add in. So we have that y equals x minus 1 all squared minus 9. And I think, maybe I'm being a bit biased here, but I think if you compare this quadratic function to the exactly same function but written in this way, and ask which one is more beautiful, which one is easier to understand, surely you would agree with me that this is more beautiful, because it kind of reminds us of the good old days when we just had x squared plus a constant. Here we have something squared, take away a constant, a number 9. Let's plot this function. We know what to expect. We know that because a is positive, a here is 1, it's positive, we're going to have a U-shaped parabola. It's going to have a minimum value somewhere. here's a really, really important point once you've completed the square. This thing that is squared, the reason this is so much more intuitive than this is the following. This thing squared cannot be negative. It can only be positive or 0. And so if you ask, given we know we have a U-shaped or valley-shaped parabola, if you ask, where is that minimum, where's that turning point of the parabola? Well, look, the smallest that y can be is when this vanishes, because this can never be negative. So the smallest that y can be is when x minus 1 all squared is 0. So this gives the turning point. Because when this vanishes, we have the smallest y can be. For any other value of x, you have a number squared which is positive, y will be bigger. So this already tells you then that when that vanishes, the turning point must be have a value y equals negative 9. It happens when this square term is 0. Well, that's just when x equals 1. So we learn straight away that the turning point is here at negative 9, 1. And we also know, because of symmetry, whatever the value of x is for the turning point must be the mirror, because this function is going to be symmetric about that. Okay. Now, you might ask, can we also get the roots from this method? Yes, you can, but I'm not going to focus on it in this tutorial. I'm actually going to look at that very briefly in a short 5th tutorial. So next tutorial, we'll quickly look at that. It's not something that is focused on at this level of maths, but actually it's there for the taking. Very easy to get the roots from here. But for now, let's just use this method to focus on some aspects of the parabola where we can work out the axis of symmetry and the turning point. Okay. Right, let's do another example. I think examples are great because you get good practice. So let's do another example. Y equals x squared plus, let's say, 6x, and then I'll just choose a number, let's just choose a number 10. Why did I choose 10? Well, the reason I chose 10 there, and I hope that is good enough. Yes, it is. I want to work out the discriminant. A is 1, B is 6, and C is 10. The discriminant is b squared minus 4ac, that's 36. Take away 4 times 1 times 10, take away 40. That's negative. This quadratic function, it will be a U-shaped one because a is 1, it's positive, but it has no roots. So you can't use anything to do with roots to figure out anything about this parabola, actually. But you can by completing the square. So let's do that. Completing the square, let me call it CTS for short. Let me just write the function down again so that I can sort of label it a bit. That constant is our bystander. We're going to ignore it, okay? For now, we're going to come back to it a bit later on. We want to focus on x squared plus 6x. And we want to write it as x plus or minus some constant squared plus a constant. And remember what I said, you just take this coefficient of x and you put it in here after having multiplied it by a half. So the coefficient of x is 6 plus 6. Multiply it by a half, we get plus 3. So you just have to remember that that's what you do with completing the square, is take that coefficient times a half and put it in there. Let's just look at x plus 3 squared. With experience, you won't need to do this next bit so explicitly, but I'm just doing it for clarity for now. This is x squared. We get plus 3x is plus 6x, and then I get plus 3 times 3. And you see this always happens with completing the square, that when you write these two terms as something squared, you get an overshoot, you get this plus 9. So we have to come in by hand and get rid of it. So this negative 9 we write after this, and it kills this unwanted overshoot. So then we can just come back to our quadratic function. We have that y equals x squared plus 6x. That's fine. We've shown that's equal to x plus 3 all squared take away 9. And then we just bring back that bystander. That comes back in, and we have plus 10. So we are left with y equals x plus 3 squared plus 1. And that is, I would argue, a much more beautiful, clear function than the thing we started with. In fact, in terms of roots, do you notice here that because the constant here is negative, we kind of know we have roots? Because remember from the very first tutorial that if you have a U-shaped quadratic function and you of the form ax squared plus c, if you have a negative c, it drags it below the x-axis. So this negative 9 here pulls it below by negative 9. Here we have a plus 1. So we know that's actually pushing it up above the axis. That's why there are no roots for this. Let's just quickly sketch this. It's a U-shaped parabola. It's going to have a minimum value, a turning point. That will happen when this term vanishes, because this can only be positive or 0. So the smallest y can be is when this vanishes. So when x plus 3 is 0, we have the turning point. Okay. So then y will be equal to 1, and this happens at x equals negative 3. So negative 3 is the mirror, is the axis of symmetry, because it has the turning point on. That occurs at y equals 1, and then we just have our symmetric parabola about that mirror at x equals negative 3. Right, so that's completing the square. You know, as I'll show in the next tutorial, just as a little sort of appendix, it's very easy to calculate roots having completed the square, and we'll just look at that really quickly. But even in terms of what you're normally asked about completing the square, which is to identify the turning point and the axis of symmetry, this is such a beautiful method. You know, it turns essentially rather an opaque, ugly object into something very beautiful and easy to understand. So I hope that was helpful, and I hope for those students that hear completing the square and shudder, that it really changes your mind, that actually this is a lovely method, and with a bit of practice becomes an easy tool to use and unlocks quadratic functions for you. So I hope that was helpful, and I will see you next time.